Hello, how are you? So this is my class on nucleophilic substitution reactions. This is my class on nucleophilic substitution reactions. Here the halogen is more negative. Here I have taken haloalkane. Is the general formula RCH2X. In this, halogen is more negative than this carbon. Okay, then the two atoms do not share. We can understand these two atoms do not share the pair of electrons equally. So unequally they will share. In such a case, what will happen? This carbon will get partial positive charge. Halogen will get partial negative charge. Here X may be anything: halogen, chlorine, bromine, or iodine. So the unequal sharing of electrons, whatever is there, this causes alkyl halides to undergo this nucleophilic substitution reactions and also elimination reactions. So these are two important mechanisms in this haloalkanes chapter. And one point I can say that this nucleophile, whatever is there, this nucleophile is attracted to the positively charged atom of carbon. Positively charged atom of carbon. So I have taken one general chemical equation part in this. It causes carbon halogen bond to break heterolytically. So this was happened. Carbon halogen bond separate out, nucleophile attached to this carbon. So shown one more example. This is nothing but heterolytic fission. Heterolytic fission is nothing but the unequal sharing of bond pair of electrons between two atoms, making the atoms charged, fully charged, positive or negatively charged species. Here the carbon became fully positively charged species called as carbocation, and halogen is separate out called as living group. So after that, the positively charged carbocation is now receiving the attack of this nucleophile, as both are oppositely charged and uniting to give the final product. Final product means this is the final product we are expecting. This is a carbocation, and the condition is nothing but the carbocation obtained in this phenomena should be stable. Then only the reaction proceeds fast and we will get the final product according to this mechanism. Okay, this is what the general in the introductory part of this nucleophilic substitution reactions. Let us see what are the important factors which influence the nucleophilic substitution reactions of this alkyl halides. Now, so let us see the first one, structure of alkyl halide. So if the structure of alkyl halide is known to us, then we can decide which type of alkyl halides undergo this nucleophilic mechanisms. The second one is reactivity and structure of nucleophile. Reactivity and structure of nucleophile. So nucleophile structure is also important. Third one, concentration of nucleophile. Concentration of nucleophile means here nucleophile whatever we are taking. This nucleophile concentration is also an important factor. Fourth, the solvent in which the reaction is carried out. Sometimes what will happen is solvent also will be introduced in the reaction. Sometimes the solvent itself acts as a nucleophile, and such a cases what will happen is nucleophilic reactions can be studied in a different way. Okay, this is our introductory portion of nucleophilic substitution reactions. Okay, let us see the mechanism of Sn2 reactions. As you all know that this Sn2 reaction mechanism, the rate of nucleophilic substitution reactions such as the reaction of methyl bromide with hydroxide ion depends on concentration of both the reagents. Here this is methyl bromide, this is nucleophile hydroxide ion, both are in the reaction mixture. If this concentration of methyl bromide, whatever is there, methyl bromide in the reaction mixture is doubled. So this concentration is doubled. So here, what I discussed is nothing but rate whatever is there directly proportional to methyl bromide concentration as well as this OH minus nucleophile concentration. In such a case, what will happen is the rate of this methyl bromide is doubled. Then the rate of Sn reaction also doubles. If the concentration of OH minus ion is doubled, then the rate of reaction also doubles. So if both methyl bromide and nucleophile OH minus, both of the reactants concentration is doubled, then what will happen is rate of the reaction quadruples. Okay. So this is what we can understand from this reaction. So what is the rate of reaction? The rate is directly proportional to the concentration of alkyl halide as well as the concentration of nucleophile also. Okay. This is the second order reaction. This we can say what is the order of reaction? The order is 2. So this is second order reaction. The first order with respect to substrate. This is nothing but substrate. First order with respect to substrate. And it is also first order with respect to the nucleophile. First order with respect to the nucleophile. So the rate law tells us which molecules are involved in the transition state according to chemical kinetics of the rate determining step. Moving on to the from the rate law, the reaction of methyl bromide with hydroxide ion. We know that both methyl bromide and hydroxide ion involved in the rate determining step. So the transition state is bimolecular, involves two molecules. So what is the transition state here? The transition state is bimolecular. Maximum energy level in the energy diagrams, and the rate constant describes how difficult the reaction overcome the energy barrier. For example, if you write the rate here using a K, the constant, that will determines how fast the reaction can be completed. So it increases, rate of reaction also increases. So the rate constant describes also one more thing, that how difficult for the reaction to overcome the energy barrier of the reaction. How hard it is to reach the transition state. The larger the rate constant, the easier it to reach the transition state. Let us move on to the important aspects of this discussion. The mechanism proposed by Hughes and Ingold for Sn2 reaction has one step only, because the nucleophile attacks the carbon bearing the leaving group. So we told that this halogen is working like a leaving group. Let us see how this mechanism will be there. So if you take OH like this, oxygen is having two pairs of electrons, is a nucleophile, and which combines with the carbon in this way. This is the carbon, and the bond between carbon and halogen is completely shifting towards this halogen. That time what will happen? So this negative charge of this nucleophile start moving towards this carbon. Moving towards this carbon. That is the main aspect of this reaction. Or you can also write in a different way, that arrow mark like this. Okay. So after that, what is the product? The product is nothing but this is OH or CH3 plus Br minus. Br minus is the leaving group. The final product obtained is nothing but alcohol in this case. So the relative rates of the reactions are quite different. Since the nucleophile attacks from the back side of the carbon, Then we have shown this compound alcohol as like this opposite configuration, inverted configuration. So we got methanol in the reaction, and we have taken methyl bromide here, methyl bromide. This is hydroxide nucleophile, hydroxide nucleophile. So what will happen is nothing but the rate of reaction attack depends on this methyl group only. So if the methyl group starts undergoing substitution with the different methyl groups, then this methyl group will become bulky group. That means the side opposite to that carbon attached halogen, what will happen, the size volume decreases. So bulky substance attached to this carbon will make harder for the nucleophile to get to the attack backside, and therefore it will decrease the rate of reaction. The example here, if I write CH2 only and one methyl group here, one methyl group here, here one halogen is there. Okay, so here a nucleophile I am taking, a nucleophile I am taking here. Assume this is hydrogen, this is hydrogen. This is one thing. So its size you can understand how the size is there. So it will proceed in a different way. And coming to the characteristic of this one is Km. K1 I am taking the rate of reaction. Similarly, I am taking another one. This is the first case. The second case, what I am taking is a nucleophile is start coming over to the carbon, So this carbon, to this carbon I am showing there are two methyl groups here, halogen is there. I am taking, this is K2. And another one, third one I am taking as the same way, and nucleophile is approaching this carbon with three alkyl groups, methyl groups. So what will happen? How the observation of rate of reaction will be there. Let us see. So here there are two bulky groups are there. Here there are three bulky groups are there over this carbon. So approach of this whatever nucleophile is there onto the carbon will be more difficult. This carbon faces more difficulty in this category. So that means whatever round part of this rounded part around the methyl group, that is nothing but there is an observation over the volume occupied by this group. So you can call this is nothing but a bulky group. Okay. So because of this bulky groups, what will happen? The rate of reaction decreases. That means reaction rate decreases. I can write one thing that K1, K2, K3 relation, how it will be there. Means here we have only one bulky group is there. And coming to the second case, two bulky groups are there. Third case we have three bulky groups are there. So what will happen? Bulky groups number increases on the methyl carbon. Obviously the rate of reaction decreases. So K1 increases, then greater than K2, greater than K3 will come in this case. Okay, this we will call it as some of the steric effects of the nucleophilic reactions. Okay, let us see the steric effect. That means this effects due to the groups occupying certain volume of space are called steric effects. That means steric effect that decreases the reactivity called as steric hindrance also. So you can indicate one also important word here is called as steric hindrance. Steric hindrance. Okay, a steric effect is definitely decrease the reactivity of the alkyl halide towards this nucleophilic reactions. So steric hindrance results from the groups getting in the way the reaction site. So obviously if you see the nucleophile is coming, onto the carbon. So nucleophile, this is a nucleophile. Okay. So nucleophile, when it is coming onto the carbon, this entire portion is called as a reactive site. Reactive site. So nucleophile is coming onto the carbon. This area, whatever is there, this area will be reduced when the bulky groups are attached to this carbon. Okay. This is why we can call the steric hindrance is one of the important factor decide the rate of reactions. As a consequence, what will happen? Steric hindrance, alkyl halides have some of the relativity reactivities are there. The steric hindrance makes more crowdy tertiary alkyl groups which is not involved in the Sn2 reactions rapid. So steric crowding in tertiary alkyl halides is too great that they are unable to undergo Sn2 reactions. So relative reactivities of alkyl halides in Sn2 reaction, we'll see the reactivity of relative reactivity of alkyl halides towards Sn2 reaction. It's given as first we have methyl halide. We have methyl halide is there, greater than, after that we have primary alkyl halide. Primary alkyl halide greater than secondary, greater than tertiary. So greater than secondary alkyl halide, greater than tertiary alkyl halide. So this can be written as CH3X. This can be written as or CH2X. This can be written as R2CHX. This can be written as R3CX. So this is the arrangement. It is not just the number of alkyl groups attached to the carbon undergoing nucleophilic attack that determines the rate of Sn2 reaction. The size of the alkyl group is also important. That is the meaning of this entire steric hindrance concept. So for example, if you take ethyl bromide and N-propyl bromide, suppose if you take ethyl bromide, another one is N-propyl bromide. So here what is our discussion is that but ethyl bromide, if you take CH3 CH2 Br it is. N-propyl bromide, if you take, this is CH3 CH2 CH2 Br. So if you observe this size here of alkyl group, that is methyl group here. Here observe the size of this alkyl group. This is methyl. This is ethyl. So what you understand from these two examples is ethyl bromide is whatever is there is size more than that of methyl. Ethyl size is more than methyl. Ethyl size is double to that of methyl as reactive in Sn2 reaction, because methyl group of ethyl bromide provides less steric hindrance. This is methyl group of ethyl bromide provides less steric hindrance than ethyl group of propyl bromide. This is propyl bromide. So which will causes more hindrance. That means ethyl group of propyl bromide causes more steric hindrance. More steric hindrance. Because of this one, what will happen? The reactivity of N-propyl bromide is lesser than the reactivity of the ethyl bromide towards the Sn2 reactions. Okay. Okay. Let us see. I am writing an equation here. This is mechanism in which nucleophile is there. This is OH minus or HO minus. This nucleophile attacks this carbon of halogen side opposite to this halogen, right? This is carbon halogen bond, and the halogen is approaching back side of that one, actually. Okay. After that, what will happen, sir? The nucleophile approaches back side of the carbon, we can see. The carbon of the methyl group. CH bond begins to move away from the nucleophile. So, here the carbon hydrogen bond also, here this is carbon hydrogen assume, that bond also tries to move away from that nucleophile and begins a reaction attacking electrons. By the time transit state is reached, carbon hydrogen bonds are all in the same plane. So here these bonds, whatever three bonds we have shown, they are all in one plane only, and a carbon is pentacoordinate. This is nothing but the carbon pentacoordinate. So how many bonds are there according to pentacoordinate? 5 bonds, looking like 5 bonds, and fully bonded to 3 atoms and partially bonded to 2 atoms. The partial bond indicated with the dotted lines, and you know this is wedge shaped structure, and here I have shown hydrogen, here hydrogen, here these full bonds. These two bonds, this is OH and carbon bond starts forming, and this dot line indicates that carbon halogen bond starts separating out. Okay. Rather than tetrahedral, we have shown one pentacoordinate structure, that is called as transition state or intermediate states. As a result, what happens? Nucleophile gets closer to the carbon and the bromine moves further away from it. So the CH bond continues to move from the same direction. So here this will move towards same direction, these bonds. Okay, and finally what will happen? Evidently bond between carbon and the nucleophile is fully formed, and the bond between carbon and bromine are completely broken, and thus carbon is once again tetrahedral in the final product. So this is tetrahedral structure and this is tetrahedral structure. So tetrahedral structure will be again obtained after the reaction, Sn2 reaction. So in this best way, whatever the best way is there, the best way of visualizing this movement of the groups bonded to the carbon at which substitution occurs is to picture an umbrella that turns inside out. For example, if you take an umbrella like this, that umbrella turns inside out. If a nucleophile comes like this, what will happen? The nucleophile is nothing but a force, wind force. Then after reaction, what we observe is nothing but, you will observe like this. Like this. So what is the meaning of this diagram is nothing but, whatever the carbon is there, that carbon configuration definitely inverts in the final product. So what is best way? The carbon substitution occurs, an umbrella that turns inside out. This concept is nothing but umbrella turns inside out. This we can call it as Walden inversion. This is called inversion of configuration. Inversion of configuration. This was introduced by scientist Paul Walden. That's why we'll call it as Walden inversion. In this mechanism, it's the most important topic. Okay. So because of that, what will happen? So there will be inversion of configurations. Obviously, takes place in this mechanism. Coming to the energy profile diagram. So we have taken free energy on the y-axis and progress of the reaction on the x-axis. We started observing how methyl bromide reacts with the hydroxide ion according to chemical kinetics. So this is the lower energy. Once the transition state formed, this is higher energy. This difference, whatever is there, that difference is more, means free energy is more. More highly unstable condition, that is called as transition state. Here this value increases, peak increases, instability of that situation increases. This is the state called as transition state. So once barrier is crossed, depending on the rate constant value, we will get final product methyl alcohol and bromide ion. So this is bromide is leaving group in this case. So this is the energy profile diagram of Sn2 reaction mechanism.